Okay, I'm going to record a new chapter on cam follower mechanisms, and there will be one more chapter that I'm hoping to cover before the end of the semester. Definitely will be a homework about the cam follower mechanisms, and we'll let you know about the content of that or that assignment. Okay, so their cam follower mechanisms are mechanisms transmit motion by the contact between the cam and the follower, most cases the cam being the input. Most people think of the engine valve opening mechanism that uses cams, but applications of cam followers are many, and I have here some examples. So one is the key lock, and there are some pins spring loaded, and the displacement of the pin by the key as it got inserted, that's the case of a cam mechanism. This is actually an animated GIF that explains how what is called well, it has a name. I'm sorry, I just missed it. Anyway, so you can see that there is some or there's an interaction between the slope parts of the key teeth and these pins, and it matters how the pin is shaped, each pin is shaped, and it matters how the teeth are sloped in order to be able to actuate them. I'm anticipating that's a matter of the pressure angle that takes place between the cam and the follower. There are indexing mechanisms that use cams used in packaging or assembly processes, and they can work in conjunction with linkages for pick and place application, high repeatability. Of course, they are hard to reprogram, but they have added reliability because of the type of construction here. So instead of actuators that are programmed, you just have cams actuating the linkages. Okay, another animated GIF showing a cylindrical cam. You may think the ball pen retractor mechanism is of this type, although it does not produce continuous motion. So again, cams have other application than just the engine valve mechanism. This is a wedge cam, we call it. It's guided by the roller, which has two side washers. These are the followers. They pivot about this point, and it's not guided. It's actually, so yeah, one guiding happens between the washers of the roller, and then there's the cable that pushes it. But we can analyze just one side, and we can assume that the cam, it moves rectilinearly. And again, this is a wedge cam mechanism example. There's the stamp mill used in ore processing, and this is a shaft that's supported on two bearings driven by a belt as a pulley. And this type of cams, they're such that contact between the cam and the follower, it happens only for a portion of the cycle. The ram, each of these rams drop under their own weights. They're heavy, and what they do, they crush ore down here below. Okay, there are ass cams used in trucks, truck brakes. On the BUV in the machine shop, we implemented an SCAM type braking mechanism, and this could be analyzed as a CAM mechanism. This pin extractor and some camera mechanisms. They use cams or at least profile slots. It's arguable. So for example, if we look at this, is the Scotch yoke. Looks like one, but instead of being rectilinear slot, it's curvilinear. Okay, so going back to the I'm sorry, we'll look at this one a little bit later. So going back to the notes, our concern will be primarily about disc cams. Okay, the 6 cases here. The 2D wedge cams could be analyzed about the same. I'm going to provide you with a copy of this paper where wedge cams are discussed towards the end. Anyway, so in terms of these cams only they can have followers that could translate or oscillate, rotate, and then the contact between the cam and the follower could be point type contact. Well, I take that back. It could be knife edge, could be roller, could be flat faced, could be other than flat, like mushroom cams. And if that curve is an arch of a circle, of course, we can analyze them, consider them as being roller type follower. The knife edge cams, you don't see them in practice. Actually, you could start with a knife edge cam, but over time this sharp edge will fill it, and you'll end up with the equivalent of a roller that is locked, or a mushroom cam, not shown here. So because of the contact stresses, they are not used in practice, the knife edge. However, they have a theoretical value, because you'll see there is a relationship between the roller follower and the knife edge follower, and we can, by just offsetting this cam either inwards or outwards, the radius of the roller, we can go between these two and satisfy the same function for the follower motion. Okay. All right, so contact between cams can be maintained due to gravity, like in the stem cam, or could be an action of a force, or could be positive displacement, like grooved cams or bilateral cams, or constant breath cams. These are conjugate cams. You'll see that cam analysis is actually the difficult part. Synthesizing cam profiles based on the desired follower motion is much it's systematic, and it's something that we'll do. So I have here, and I do have working model that I can play. So this is a going to the chapter and looking at the. So I do have some working models that go with this. So okay, so in working model you can use a closed, like this one, and you can map it on a disk, and you can have a point now being constrained along this closed curve, like you see actually done already. So this is how you can model cams in working model. You can see it in an attempt to copy the profile of an existing cam. I think it's what I did, although the measurements were very accurate using an engine cam. You can see how noisy the velocity and acceleration in particular is, or are. If you instead use, so I could go and replace this smoothen, was just 3-4 control points that I did. Motion would be, let's see, can we do it? So motion would be much smoother. Okay, so only 3 control points, and what I did was to go on, join, and you'll see now that it's much, of course, follower motion is totally different, but it's much smoother. Why is that? Because I have a spline done by the software, generated by the software between the 3 control points. But if I have many points, then air will translate into that noisy appearance of the less the displays, more velocity and acceleration. Okay. So yeah, one way of doing it. Not that you couldn't model cams with unilateral contact, and what's going on? It was working last time I was here. Sorry for this. I do have others. Hopefully there. If not, I do have backup copies. All right, so here there are some adjustabilities. I could change the amount of offset. So this is a face, flat face follower, and I could change the Y offset. For example, I could make it 0.2, or going negative 0.2, and I need to help the software start from where a contact is made. So I'm using the anchor, hold this, run, and wait and wait and wait and wait. This doesn't change. I have stop, and then you start here? There's an option. Start here. I delete this, and I hit run, and I could check the effect of changing that eccentricity. So there are versions of the mechanism from previous simulations, and this is how the velocity, the displacement, let's see, erase meter value, and it looks like I need to make it auto, and hit run, because it was outside the limits of the graph that this was original. Now look at the force. This is the contact force, and the contact force has there's no friction, so I'm not talking friction and normal force, reaction force. I'm just talking, so neglecting friction. The normal force that exists in the contact between cam and follower, and this is always perpendicular to the face of the follower. Now, important parameter in cam analysis and in the cam design and cam mechanisms, is the pressure angle. So I'm going to take this into Paint, and we're going to look at the what the pressure angle is for this mechanism. So pressure angle is the angle between the force at the contact point and the velocity at the contact point. Velocity at the contact point will be perpendicular to the line. Let's make this smaller or thinner. Okay, so now I'm trying to draw, you're not seeing this, but I'm using a post-it note to draw a normal or a perpendicular line between the two. I should have left it as it was. Okay, so I'm trying to draw a line that is perpendicular to the line that connected the contact point with the pivoting point, and this will be the velocity. So I have the velocity vector, and again this was 90 degrees, and so this is 90 degrees. Okay, and the angle formed by the two vectors, the force vector and the velocity vector, this is going to be the pressure angle. And I believe previous chapter we used phi, or was it gamma? Literature varies in terms of the symbol used. But in any case, pressure angle is defined as the vector or the angle between the force vector, Norman, or at the contact point, and the velocity of the contact point. Okay, let's see if this returned to better feelings. No, and I'm sorry for it. Let's see this one. Well, this is the one that we looked at. Hadron. Here we have the software that is allowing us to represent. I'm sorry, I need to look back. So the software allowed us to represent both the normal force as well as the, let's see with this one. So I take screenshot, print screen, and go back to Paint, and we have the case of our lower follower, but we'll be looking at what color would be a good color here. So we're going to look at the angle that is formed between the normal force at the contact point. Okay, so there's the contact point. It won't be the velocity of contact, but rather the velocity of the center of the roller. So this is going to be the pressure angle gamma. Velocity of the center of the roller for a translating follower, it is of course going to be, for this case, vertically. Normal force at the contact point is going to have the direction of the connecting the contact point with the center of the roller. This will be the common tangent, and the common normal has a direction of the center of the roller. Okay. And then the last example is where, and here again we cannot represent the velocity of the contact point. Before was possible because we're looking at the velocity of the center of the roller, but otherwise you cannot plot the velocity of the actual contact point. The software does not allow that. Okay, so here we have the contact force is normal to the face of the follower, and the velocity of the, I could use one of these, the velocity of the, I could, but I'm not. So let's use this and a line, and the velocity is going to be the, will have the direction of the translation of the follower, and this will be the, by the way, I have quiz and exam questions where I'm asking students to plot to show the to show the pressure angle in cam follower mechanisms. Okay, so again, this is the velocity of the contact point. This is the force, and the angle between the two is going to be the pressure angle. You recognize, because this is always the same angle, 90 degrees, and because the force, contact force, has the same direction, velocity vector has the same direction, and this is actually going to be constant. Wow, constant. Again, this is 90 degrees. And of course, if the angle here is 90 degrees, it's not right now, but for that angle, the follower face angle, 90 degrees, this gamma is going to be 0. Okay, so this was pretty much what I wanted to say about cam follower analysis. The pressure angle, it's influenced by, for a given cam, you saw if I change eccentricity. But usually we start with the follower motion, and we want to see what the cam shape should be for the follower to do the perform the desired motion. Okay. All right. So you saw in the analysis simulation graphs of the position and velocity and acceleration. Actually, in cam design, there's the derivative of the acceleration that's also of concern. You want the acceleration to be finite, and you also want the jerk to be finite in case of high-speed application, because infinite accelerations theoretically translate into very large contact forces that cause wear and noise, and again, we want to limit those, as well as their derivative of the acceleration, which will be it's called jerk. Okay. All right. So before moving forward, you may want to try on your own to draw the. Maybe I should do it for this one because the working model was not cooperating. So I'm going to take a screenshot, and I do have the simulation hopefully working elsewhere, but I'm not going to look it up like right now. Select all. Let me delete this, and so let's look at the pressure angle of just this one. Okay, what I wanted to do, copy, and then select all, paste, and let's see, can I enlarge it? Acceptable. All right, so what is the contact point? Contact point is like right here, and I meant to, so contact point, the common tangent is going to be, I'm doing my best, so it's going to be this one, perpendicular, and it's through the center of the cam. It's going to be the force. Okay, so this is the force, and I'm now switching to blue color, and I'm going to represent the velocity. So you get the velocity, connect. You connect the contact point. I said we're working. I'm taking that back. So we're working with the center of the roller. So I'm connecting the center of the roller with the ground joint of the follower, and I'm showing perpendicular the velocity vector. Okay, so the angle between the two is going to be gamma, the pressure angle. Okay, so contact force go through the center of the roller of the follower. We take the velocity of the center of the roller, and then the angle between the force vector and the velocity vector is going to be the pressure angle. I'm certain you can do for this cam, could be also oscillating roller, as well as for the other ones shown here, similar analysis. Okay, so more on some nomenclature about cam follower, this cam with followers mechanism, and this one is a translating follower with a roller. And we have in yellow the actual cam. We have what is called a pitch curve, and it's the curve that is traced by the center of the roller. And you recognize, I'm sure, that the cam profile is the offset, inner offset, like in AutoCAD, of the pitch curve by the amount r equals the radius of the roller. We're having the base circle when the roller moves along the this portion of the cam profile, that is the base circle. There's no displacement, although it can be missing from some cams. And then we have the base circle, like in all right, so pitch point, base circle, yeah, base circle, and then we have the major circle. The major circle, it's through, although it's not shown here, we can imagine a circle that goes where it's an extension of the circular portion of the cam when the follower is in the maximum displaced position. So those are the dwells of the cam when the follower is running over the base circle, or the major circle, if we call major circle the actual cam profile, or the circular portion of the cam profile corresponding to the upper dwell. Anyway, so the follower is motionless. In between we have the rise and the return. Again, depends on the direction of the cam. So if I rotate this cam clockwise, I'll have, you can see here, a smoother, longer transition between the two, the base circle and the major circle. And then the return is a little bit faster. And it matters really, because the working against the inertia of everything that I'm driving would be during the rise of the, again, assuming the direction of rotation of the cam is clockwise, like I said. If I reverse it, I have a faster joltier motion of the follower, and that is associated with higher acceleration, higher contact forces. On the return, though, is not as big the concern. You don't want to retract too fast. If it's spring loaded, then you want the acceleration induced by the spring to be enough to where contact is maintained. If this is gravity, a low contact is due to gravity, like a stem mill, you don't want the acceleration, theoretical acceleration of the return, to be higher than the acceleration to gravity, because there will be loss of contact, which actually happens on purpose on the stem mills. Okay, we'll look at those. So we're going back, and here is not quite obvious, but if we look at other stem mill mills, then you would see maybe this one. This say open a new tab, and I can make it bigger. So you can see how the cameras look. The direction of rotation is this one, and there will be a point where the contact is broken and the follower just drops under the effect of gravity. So this is the way this works. But in other instances, you do not want the theoretical acceleration to exceed the acceleration at which the follower could come back under the effect of the spring that is used to maintain contact. Okay. All right. So I already anticipated that it's important how blending between the two circle, the base circle and the major circle, if we call this the major circle, although it's labeled as the major circle, the one on the peach curve, but it could be one on the major circle on the cam profile. So it matters. And there are a number of examples that I usually tell students. So for you're on a car, you're on a secondary road, or maybe come from a driveway into the main street, and if there's not a good blend between the two, and if the car is fast enough, you can hit the asphalt with the underbelly of the car. Or if you're riding on an elevator, you want to have a smooth transition between no motion, the start of the elevator motion, and when the elevator reaches the destination floor. All right. If you go on a construction site and you ride one of those moving scaffolds that are motor driven, there'll be a lot of noticeable jolting when it starts. It'll be noticeable jolting when it stops, but that's of course not the case with well-designed elevators in public buildings. You sense as the rider the lack of comfort. For the follower, cam contact, it translates into, don't forget, force is mass times acceleration. So you're accelerating the follower, and if the acceleration is very large, theoretically infinity, you will have large contact forces that will cause wear and sound associated with those impulsive forces and vibration. Okay, so you have usually you define like how long in terms of cam displacement, cam rotation angle of the cam should be the upper dwell, how long will be the lower dwell, and then how you distribute the rise and the return, and how do you program the motion of the follower between the two. You can have no upper dwell, you can have no lower dwell, or you can have no dwells at all. For engine cams, you don't have an upper dwell, you have a lower dwell. For a cam that drives a membrane pump, there is not a dwell at all. The eccentric cam that we looked at with other occasions. So the eccentric cam, it's one that it's one where there's no what I'm trying to do, I'm trying to hold this and I'm trying to bring these two in contact. I stop but don't reset, go, and it says start here. Delete this, and I have an eccentric cam. This is producing sinusoidal motion and position, velocity, acceleration in the y direction. and was a little bit of impacting at the beginning of the motion, but otherwise this is continuous smooth motion. So again, what you saw here, it's because of the I could alleviate that actually, so I could further wait until it settles, and then again we have start here, take this off. Let's see if it behaves a little bit better. No, not really. It's probably because at the start of velocity of the follower is not matched the actual velocity. But past the transient, you have smooth continuous motion. Anyway, so this is an example. Long story short, this is an example of a cam follower mechanism with no dwell, just rise and return. Okay, so question is how we are going to program the rise and the return motion. And for this, there are standardized functions. And again, you'll have access to the notes, and this is the cam angle, and you as a designer decide whether the rise or lift is going to happen over the 30 or 40 or 50 degrees of cam rotation and return over 20, 30 or 40. We say that return could be fast, happen in small amount of or degrees of cam rotation. You see here we have some start, so S as displacement. This could be linear displacement as well as angular displacement. So here it says follow displacement, but could be in units of angle, or could be units of degrees or radians, or could be units of inches or millimeters, centimeters, meters. Okay, so L is the lift, and it says it starts from 0. If you're measuring from if you associate a reference frame, this 0 will definitely be above a horizontal through the center of the cam. And so yeah, for linear lift or return, once you select the amount of cam angle for the lift or the amount of cam angle for the return beta, and once you know the amount of lift, then this would be the equation of the follower displacement. Usually the 0 angle associated with the beginning of the lift, but the return is not associated with 0 of the cam angle. So that's why this is theta start. So you need to do a axis translation. So in order to get theta star, or the actual theta, you would need to, maybe you could screenshot in class, I would have written on top of this. So so what we have is, and I need to use the okay, so we have the angle theta. Wow, quite a theta. So we said it starts at 0, and it's fine. We have this would be the angle beta for the lift, for the lift. But for the return, this would be the beta for the return. Theta star in the table, it's assumed to be equal 0. So how do you get theta star from theta? You just take theta star, it's 0 at this position, and increases until you get beta at the end of the return. So in general, and you take this off. So in general you say yeah, it's worse than eating with chopsticks. I have the same. Okay, so I have theta star equals theta, which begins with 0 here, negative this whole angle. Okay, let's call it for convenience delta theta. Okay, so this is how you do the change of variable, and how you could use the second equation by just doing a change of variable. But really, linear motion between 0 and the end of the lift, or between the lift and 0, would be these two equations. Parabolic motion, constant acceleration. Things to comment here is that at the beginning and at the end of the follower motion for both the return and the lift, we have infinite acceleration and infinite jerk. These are not good follower motions for high-speed cams. For slow-moving cams, maybe. Parabolic motion, constant acceleration. This is where we have a better blending in. As you can see here, the jerk is infinite, acceleration is finite. Still not the best best follower motion for high-speed cams. The lift is sort of the return, the fall. As you can see, they are piecewise continuous, and they are defined based on where I'm at with current angle theta. So between 0 and half of the duration of the lift or the return beta, I apply this equation, and this would be the second equation to use as theta goes between beta divided by 2 and full beta. Again, it will be up to you to decide what the duration of beta will be. You decide how big L should be, and then the last concern is how do you, not the last, your other concerns. Pressure angle is one of them. Size of the cam, material selection, you know the drill. And the again, the way you blend in the lower dwell, upper dwell, it's based on the follow motion that you select. And I said this is still not the best one for fast rotating cams. Modified parabolic motion. Modified parabolic is a combination of linear motion with a parabolic start and parabolic end. And this one too has infinite jerks, as well as where transition happens between the parabolic and the linear portion of the cam motion. So this is the linear part, this is the parabolic part. You see the power 2. And you would choose the amount of it's somewhere in the text. So you choose gamma between 1 and 2, and gamma divides the duration of the return or the lift such that you have uniform motion in between. If you have gamma equal 1 or gamma 2, then there's no uniform motion in between. So this essentially vanishes. This in-between term vanishes. Harmonic motion. This one provides infinite jerk, finite acceleration, and The jerk is infinite at the beginning and the end of the follower motion. And these are the equation for the lift and for the return for the fall. Cycloidal motion, this one is producing finite jerk, zero acceleration. Before, the acceleration was finite but not zero. And yeah, you'd say this is a good candidate for high-speed cams. Thing is, there are other type of follower motions, higher order polynomial, using splines. People still look for the best follower motion for high-speed application, like high-speed engines. Don't forget there are variable timing engines in use. So there's still work left to do about cam designs, really. Okay, so there's more to it, but here they are. There's a homework assignment where we'll have to implement these equations for the amount of lift and for the amount of rise and return given, and also the amount of upper dwell. And there are a number of, or rather two approaches to generating the cam profile. One is using equations, and I'm not going to consider those. The other one is using a graphical method, or a better name to it would be, heck, I don't like to, and you see all my formatting. So the other one is called graphical methods using motion inversion, where not for you're hearing me using this word, so motion inversion, where the follower is rotating around the cam in opposite direction, like the cam is rotating, and you're recording relative to a slab that will form the cam. We used to generate the cam at the end. The multiple envelope follower, and those envelopes, or the multiple. Heck, I know why it's 10:15 in the evening, p.m. So best is to just go to a working model and show you the motion inversion. How is it going to work? And I go to the so we had this one. It didn't work. Yes, but I can go with the other one. Okay, so what I can do is to apply motion inversion. I'm going to go and say new reference frame, and it should be on the cam. And if I run, I see now the fellow moving around. Okay, this is one. I'm going to say window appearance and track outline, and I'm going to say word tracking every frame, and I hit run. Maybe every frame is too dense. Tracking every 4 frames. Okay, so, but of course there's a cam there, and the cam is the one that it's causing the follower to move. But if I would put a motor here that drives the follower the way I want, and if I take the cam off, then and again, assuming that the follower is driven the way it is intended to, its envelope is going to generate the desired cam. So you have the cam as an envelope. You figure out a way how to extract this contour, send it to a plasma cutter, laser cutter, or numerically controlled machine, and you have the cam. I actually do have some working models that do follower motion with the follower being carried by a slab. And you see here, so it's not like before, it's not a trick, it's not a cam that's there, but it's the follower that moves in accordance with, and you can see here it's linear, some dwell in linear, so linear rise, linear lift, linear return. I can control a number of parameters. I can control the radius of the roller. Let's see, racetrack. So if I make it 0.5, actually no, that's the an initial radius of the. So make it 1 back. There's the roller too that I can change. I can make it 0.4. Make a bigger roller. An offset, there will be, so let's make it negative 0.5, although it's arguable which is negative, which is positive. So roller radius, and then I can control, these are angles in radians, the amount of rise or lift, and when the upper dwell ends and when the return ends. So I could make this 1.2 radians. This stays as is, and I can expand this to let's say 5 radians. Okay, and I hit run. So it'll be faster rise in prolonged return. The cam profile changed. Okay, the bias, follower bias. So it not starts at 0. I cannot have a cam of 0 minor circle, or was base circle called. I can make it smaller, and if I have it smaller, I'm going to probably see what it's called undercut. So yes, you can have same as with gears, you can have a situation where the cam comes back over a profile that was already generated, and say you in good faith you generate this cam the way it's shown here as follower envelope, but if you're to put on the machine, you will see that it's not going to generate the desired motion because of the undercut. Okay, so let's go back to 1 and let's change. Well, run it one more time, and you can tell where the events happen. So here's the end of the lift, and this would be the beginning of the return, right? And you can tell the change in the curvature and all that. So this is, remember, blending the driveway was the main road, or a secondary road was the main road, and you come too fast, and or maybe a speed bump. It's not blend into the street, and if you drive too fast, you can damage the underbelly of your vehicle. Okay, so I'm going to change now to a different motion. I'm going to take this, just copy this, and I'm going to go to the actuator, and this is the long equation here, which is the first of the equations, corresponding linear displacement, and replace it. And now we're going to have the same parameters, radius of the roller, and when the dwell starts, where it ends, and rising. So same phases, but the blending in, it's visible on the shape of the cam. The blending in is visible on the follower motion. Yeah, these are the velocity and acceleration. You saw earlier, I haven't pointed to, you can go back into and watch the video a few minutes earlier, and you'll see the jumps, the spikes in acceleration at the beginning and at the end of the lift, the beginning at the end of the return. Okay. All right. I do have other ones. This is with oscillating, and it's already on harmonic displacement, so oscillating follower. Likewise, you can adjust the phase angles for the follower motion as well as roller radius. The offset would be okay, so this is the offset, and then I have another offset, negative 5.5. I think it's limited to 4.5. Doesn't go any further. Yeah, but I can make it smaller than. Okay, so these are parameters that I can work with, and I could do these towards improving the pressure angle. The bias, so this will be initial alpha, it's 25, you can see it starts lower. This controls the size of the cam for a given rise, 0.2 radians. And okay, and then all sorts of adjustability that I can play with. So size of the cam, as well as the pressure angle, as well as the undercut. And if nothing else, you can of course change the follower motion. A linear displacement or linear follower motion is more prone to undercut than a higher order one. I really want you to see an undercut clearly. See this one. So I do have, this is the harmonic smoother. Let's see, do I have one? I think this last one was with flat face follower. You can see the frames are or every several frames I take the envelope. But if I do go to a linear displacement, alright, so this would be for the motor. Huh? I said motor. How many motors do I have? I have 2 motors. Okay, this one. So I change to linear motion, linear display, yes, and then and of course there are graphs which you cannot see because they are outside of the recording area. Okay, but I want to induce an undercut. So let's see if I make this really like 0.05, and maybe you'll see how it cuts over itself. Okay, so it looks like we've got it somewhere where the follower, it's long and it's extended and cuts over the already generated profile. So if you see a lengthy linear portion of how to make this bigger. So if you see in word tracking every frame, okay, world accuracy, and I said yes, world accuracy 0 1.5. Okay, so if you see a portion that is straight, and I could increase this by changing to an even smaller, so end of the, let's see if I make this 1.5 instead. Yes, so this is you know, if you see straight portions on the cam profile resulting from the envelope, that's a sign of the undercut. Because if I'm to cut this cam disc out of stock and have it to operate with the follower, when the follower, flat being the face of the follower, is going to engage this portion of the cam, it makes contact here and then jumps to a contact here. So clearly it's not going to generate the desired follower motion. This is again the theoretical one according to this equation, using these as input. But the actual disc cam that results by enveloping the follower, it's not going to look good. If I make this 0.02 even more dramatic, yes, it was, you know, some areas of undercut as well as these straight portions. So the remedies is to increase the base circle of the cam, that is, add to the bias for the same lift. And so you can see here it's smooth shaped. Let me make it bigger. He'd run again. Oh, I said sorry. So now it's smooth. The shape of the cam is smooth. No straight portions. So we took care of the undercut, but that affected the size of the cam on one hand, and then secondly was the pressure angle. It's going to be likely, although it's never displayed, it's not part of the analysis. So the pressuring is also going to be affected. As usual in mechanical design, there are trade-offs, and you never get the best solution from the beginning, unless you have a lot of experience. Okay, so I'm closing this, and let's wrap up. Usually in class we spend 1 hour and 15 minutes. I have 13 minutes. So let's look at what's left of the notes. These are derivations that allow us to, using vector method, to derive the equation of the follower in a motion inversion situation. So this is the motion inverted mechanism for a translating roller. If we are given the eccentricity of the cam, if we're given the follower motion as the displacement of the linear actuator, you know, starting with the vector equation, you project over x and y. You can also calculate a base circle, and this gives you xb and yb of the center of the roller in the motion inversion. So for given theta, given the associated s, you find xb, you draw the circle corresponding to the roller. Of course, recording just xb yb will give you the pitch curve, and that pitch curve is the actual cam, in case your goal is to design a knife edge follower with a rotating cam. Alright, so equation for xb and yb. If I have a translating flat follower, I would be interested in, and here I have a fixed angle alpha. In many cases this is just 0. I want to know how big and it matters if it's alpha other than 0. It matters how much offset I have, the way it's stated, you know, going with from O to A to B and then to C, in order to just draw the BC line So that's the goal. What's the B and C coordinates in order to draw this line? And you'll see it's using MATLAB or Octave. Okay, so again, S is function of theta, motion inversion, follower envelope. So equation for XC and YC. Equation for B are actually these here. And then we have the other two cases where I have a roller follower that oscillates. So it will be phi as function of theta. Likewise, I need to know what XB and YB are for various thetas. And the corresponding phi. Again, phi is follow motion. The way is, just to put it in perspective, so the way it was gotten here, decided how big the L would be, the follow rise, duration of the rise, or amplitude of follow motion, I meant to say, not duration or amount of rise. Okay, so those angles, 0 was theta 2, theta 3, I think the way I had them in working model. Anyway, so you have the follower motion. You need to start with a bias in all cases. So that will be part of the follower bias, that it's included with the S, the follower motion. And the follower bias determines the base circle of the cam. A smaller bias reduces the circle, a bigger bias increases that circle. On top of that bias happens the follower amplitude motion, or happens that amplitude motion of the follower. Okay, and then we were looking at this one. I'm interested in XBYB. Again, write the vector loop going from O to A to B equals OB, and a vector OB has coordinates XBYB. Of course, I need to know D, I need to know W, the center distance, or center distance. And then finally, the flat face. So would like to know here point B and C. Okay, there's eccentricity, center distance. Phi is measured this way. So how is this going to, XB and YB is function of theta, WE, and phi in order to do motion inversion, other than using working model. And here they are. Okay, and this is the case of a linear rise, some dwell happening between 90 degrees here, whatever, and a higher order return. I think it's harmonic, return. And this is how this the follower envelope for a translating follower with roller and with offset is going to look like. Okay. So draw the pressure angles. Now the assignment, it's still not yet 1 hour and 15 minutes of recording. The assignment would be for you to, it's going to be issued tomorrow and not too long. But you're going to really use as a reference this paper of mine, and you'll see that was because they imposed the limit of 10 pages. So you'll see that what I did was to merge the flat face with the roller face follower. So instead of having 4 separate MATLAB programs, I have only 2 plus 1 more for the wedge cam, and then oscillating follower, and then translating follower. So translating follower, oscillating follower, and wedge cam. So 3 programs, rather 4, because there's oscillating and translating roller followers for the wedge cam, but this is not of our or your concern, our concern for this class. So I'm going to supply you with these programs, although you could take them off the paper itself because they work. However, I'm going to supply you with the MATLAB code that can be run in Octave. And if you saw an Octave in my browser, was because I was about to or was planned to let you know that by just going to you Google GNU Octave, that's it, search, and you just download and install on your computer the software. Of course, has to be for the Windows, and I'm assuming you're having one of these newer Windows 64. All right. And no, and the way it looks, command line and graphic user interface. So it looks very much like MATLAB. It's the window is organized different in terms of, I think they are not even, they are pretty good similarities. So 2020 file, open, and again these will be the Octave compatible sources that I'm going to supply with. This cam oscillating follower. Okay, so this is the source code, 2 of them, and here's where you're going to make the changes, the bias, and don't forget that the reference is actually going to be this paper, because I combined in the notes. Actually, for the future I'm going to separate them back, but in the notes, and the way they are in the notes, and I'm going to have 4 separate MATLAB or Octave codes. But again, just to limit the number of pages, I had them combined. So if it says flat face follower, you just make the roller radius 0. Okay. And of course you're going to now reduce. So if it's just a roller follower, you don't need CB to be angle alpha should be 0. CB does not have to be a BC or CBS, so it can be 0. You make it 0, but should be with the roller. Where is it? So you say here roller, it says choose from flat and roller, and if it's roller and you make the roller 0, it's going to actually consider an IFH case. Anyway, so let's look at this running. Change directory. And what it does, it's well, this is not MATLAB, but it's pretty decent otherwise. So what it does is reading from a text file that you are going to generate first in Excel and then export to text. So it's reading angle theta and follower displacement, and then you select the follower bias, you select the other parameters, roller radius. Again, you need to reconcile these with your design, and it's going to do for you the cam profile like so, even showing the roller in the initial position and the follow. I said I could, so if I change this to flat, it's going to record for the same follower motion, not a roller, but rather a line. Okay, I don't know why it's trimming at the, yeah, it does. If you want to see more of it, it's something that MATLAB takes care of automatically. So let's see, where's the second figure 2? I could make this 3. Oh, it's because the no, that's base operations. So it's not going to be, or be trimmed at least less. Okay, so we have now the envelope follower envelope for a flat face follower. I did not represent the roller, and the program distinguished based on the value of follower type. The program distinguished between the two and took care of, you know, enveloping the right. The other one is I passed 1 hour 15 minutes, but I know you can watch the YouTube in over the course of a full week. So I'm going to open file, open. It will be the other one, this cam. So that one was oscillating translating file. This is a different text file. Let me show the text files. So it was MATLAB, and all right. So for this is the text file that was used to drive the follower for the first program. This is the angle in degrees. Okay, 0 to 360, and this is the follower motion. One would be with, I think I have linear. The third column is for harmonic motion. I could go back here and change to where instead of from column 2 it reads column 3. I haven't tried this. Yeah, so you saw instead of that linear rise and return, now the follower motion is was it harmonic? Okay, and then going here for this other case, I have just 2 columns, so theta and follower displacement. Again, they come from Excel, and they were exported to ASCII. In the paper that I'm going to provide you with, if you have access to MATLAB, feel free to use the MATLAB code and directly Excel for Octave. Octave, you would have to go with the programs that need to read the text files. Okay, so let's go back to Octave. This cam translating follower. I think we hit run. Not yet. And here, hopefully it works. Yeah, it does. So here I have a non-linear but harmonic follower motion is harmonic, or non-linear for sure. And it even shows the axis of the follower, so you can tell the offset and the roller in the original position. Okay. If I change the roller to flat, okay, flat, and there will be an angle. So this, I can make this 0, or it's 10 degrees, and with sine. Oops, what's going on? Yeah, well, I would need to follow face length. Okay, it can be 0. So I need to have a follow face. Yeah, that was it. And you would need to make it to where, long enough to where it envelopes. Now it's too long. But it got the cam profile for us. Okay. So, yeah, probably a better length would be only 5. It's not bad. The Octave for a free tool, and yeah, so we've got the 10-degree clockwise. Offset matters. This offset matters if I have an angle, but if I other than 0. But if I change this to 0 offset, it doesn't matter. And it looks like I can make this a bit shorter. Okay. So these two programs and the problem statement, where you need to generate first the follower motion, and then secondly we're just going to produce the cam profile. So that will be the assignment. This being said, I'm going to stop recording. It's almost 11 o'clock p.m. and see you next time.